Hi, I'm Gaia, and today I'll talk you through my poster presentation that I presented last December at AGU in New Orleans. The poster presentation summarizes the research that I've been doing during my first year of PhD, and it focuses on global stochastic flood modeling. More specifically, it focuses on how we can use discharge data from global hydrological models in stochastic flood modeling. So in the next few minutes, I'll give you an overview of my work. So the first question we'll have to answer to is, what do we mean by stochastic flood modeling? So while typical flood models simulate hazard maps that have a constant return period in space and do not take into consideration the spatial structure of flood events, stochastic flood modeling allows us to simulate realistic flood events with spatial dependency between different sites. So this means that, for example, when we're looking at the risk associated with a 100-year event, instead of simulating a 100-year flow everywhere in our study area, we simulate many different events and then look at all of those that have a return period of 100 years. So this approach is very useful, especially at large scale, where spatial dependency matters the most, as it significantly improves our accuracy in assessing flood risk. One of the most time-efficient ways to do this, to do stochastic flood modeling, is to derive the spatial dependency between sites using historical discharge data, and then using the stochastic model to simulate realistic events. So while this works very well for data-rich areas, such as the United States, it isn't applicable in data-scarce regions, since we need to have historical data. This is where global hydrological models come into play. Since global hydrological models simulate river discharge globally, they could be used as input to the stochastic model instead of historical records. Using simulated discharge to derive the spatial dependency between sites would allow us to use this approach globally. So this method has been tested already in the United States. It has not been tested globally, and that is what my research focuses on. To test this methodology, we first need to retrieve global gauge data, and in this case, we are using 2 global daily discharge datasets, and then identify which regions we want to analyze based on data availability. So the idea is to run the stochastic simulations with the historical data, then with the synthetic discharge from hydrological models, and then compare the results. First, the data for each region is extracted and processed, which means that any site that is not suitable is removed, or any infilling that is needed is done. And then we run the stochastic simulations using the historical data for each region. After that, simulated flows are extracted at the same locations from global hydrological models, and then they are used as input to the simulations. So in my research, I've been looking at 2 hydrological models, PCR Global from the University of Utrecht and Camouflage from the University of Tokyo. And finally, the 4th step is to compare the results between the 2 approaches. So on the map on the right, we can see the different areas that have been analyzed in this study. And the selected case studies are in Australia, Malaysia and Thailand, South America, Africa and Europe. The performance metrics that we use to compare the results obtained with the 2 approaches are the co-occurrence rate and the co-occurrence rate error. So the co-occurrence rate is the probability of an event occurring at both neighboring and conditioning sites at the same time. So for each conditioning site, the co-occurrence rate is the probability of the neighboring site, J, experiencing an event with a return period that is greater or equal to a certain threshold when the conditioning site is facing an event of a certain return period. So this can be calculated with different return periods, different thresholds. But for example, if we were looking at the COR 520, that would be the probability that the neighbors of a certain conditioning site experience at least a 20-year flow while the conditioning site is experiencing a 5-year flow. And the co-occurrence rate error is the root mean square error between the observed COR and the co-occurrence rate obtained using synthetic discharge. So on the right here, we can see the results in terms of co-occurrence rate error in the different areas that have been analyzed for the two global hydrological models. The conclusion that we can draw for this is that we can say that the general performance of the model-based approach is promising in most of the areas tested so far. So the median co-occurrence errors in most regions do not exceed 25 percentage points, which is a value that is comparable to the results obtained by previous research carried out in the United States, here at Fathom by Oliver Wing, which errors were around 20%. So in the United States, the loss distribution obtained with the two methods were almost identical with this magnitude of errors. And the fact that the errors in these areas are similar in value suggests that this method could be used elsewhere, even if we have not calculated the losses in all of these areas. So the results from this research at present day suggest that we could use discharge data from global hydrological models to derive spatial dependency in stochastic flood models. And this would allow us to design a synthetic gauge network to use and generate event sets with detailed spatial dependency in data-scarce regions at the locations that we're interested in, and also evaluate losses where we have exposure data. Future plans for this research include developing such a stochastic model in a new area and potentially looking at the losses, and eventually explore how climate change could affect the spatial dependency of flood events. That was the breakdown of the research I presented at last AGU, and thank you for your attention.